What's the difference between a poorly dressed man on a unicycle and a well-dressed man on a bicycle? Attire. Like I said yesterday, before we can do too much with logs, we have to build up our knowledge of logs. So yesterday, just the basics, how they're written, how we can go from logarithmic form to exponential form, use that to solve, or at least the basics of solving for what we have right now, natural log, common log, and today we're going to add in our properties of logarithms because we can actually condense and expand logs using multiplication, division, and powers. So the reason that we can do this, all of our expanding and condensing comes from what a log is. So yesterday when we had something simple like this, we're going through what that log is actually meaning, this log base 2 of 8. If we are answering this question, what this log means, our answer is an exponent. It is asking us 2 to what power is 8, and so our answer is 3, and 3 is an exponent. So really important here that since logs are exponents, they behave like exponents. So you'll see what I mean in a minute, but our rules that apply to exponents also apply to logs because whenever we're answering that question, what is this log? Our answer is the exponent of 3. So we'll start with multiplication. I'm going to start with the exponent rule to start with, make sure you remember that, and then show how that relates to expanding a log. And then when we're done with all of the rules, we'll go backwards and go from something long and condense it. So starting with multiplication, what we're talking about is having the same base to different powers, and we're multiplying something like this, an x to the third times x to the fourth. And in the case when we're multiplying same base to different powers, well, it doesn't have to be different powers, they could be the same. We end up adding the powers. So if I'm multiplying, I would end up saying x to the 3 plus 4, or x to the 7th power. So if I am expanding a log, and I have multiplication happening in the argument, so in this case we're saying u times v in the argument right there. The rules of logarithms, the properties, tell us that because this is an exponent, that I can expand it into addition. So same reason that we had multiplication here and I ended up adding the exponents. I am multiplying in my argument here and I can expand. So log base b of u plus log base b of v, I can expand it into addition. Anytime I'm expanding or condensing, the bases are going to be the same. So if I am expanding, this base b still is there. If I'm condensing, they have to have the same base before I can condense it back into multiplication. So if I went the other direction, it would take addition and condense it into multiplication in the argument. Our second property is division. If I have the same base raised to powers and I am dividing those two bases raised to powers, we end up subtracting the exponents. So I've got an x to the 5 minus 3, or you might think of it as canceling 3 of them and then you're left with 2 on the top, but what you're really doing is subtracting the exponents. So very similar to multiplication, if I see division in the argument, so on my log base b of u over v, then I can expand into subtraction. So I would have log base b of u minus log base b of v. Now for this one, it does matter which order I go in because I am subtracting, so it does matter which part of that gets the subtraction. The numerator is always first, and then we're always subtracting denominator. Okay, so to put together our two properties that we have so far, we could have something we're expanding like this, so 4x over 5, where I'm dividing my 4x and 5, but my 4 and x are being multiplied. So I can expand all of that to where I have all three of those, well, two operations, three logs happening when I expand. So if I start with the division, that's easiest to start with because these go together. I would have my log base 2 of 4x minus my log base 2 of 5. And this might be helpful if I was able to actually calculate part of it. So log base 2 of 5 is not one that I can do in my head, but if it was like log base 2 of 8, we could say, okay, well that part's 3, and that might help what we're trying to do. Eventually we'll use these properties to solve logarithmic equations, condense them or expand them in a way that's helpful for us. From here, I can still go further. My log base 2 of 4x can be expanded into addition since they are being multiplied. So completely expanded, I would have a log base 2 of 4 plus the log base 2 of x minus log base 2 of 5. And we want to make sure that anything that was in the denominator is being subtracted, anything in the numerator was positive to begin with, or whatever sign it had to begin with. If it was negative, it'd be negative. So that we can tell if I was going back the other direction, this is the only part that would be in the denominator. If it had something it was being multiplied by, say there was a y there, then we would have minus log base 2 of y, so that we would know both of those go in the denominator. They both have subtraction. With expansion, sometimes it is hard to tell when you are done, so I would just say you're done expanding whenever you don't have any operations left in the arguments. So looking in your arguments, look to see if you're multiplying anything, dividing anything, or if there is anything raised to a power, which is our last property. This is not as important that we know when to stop, because eventually we will use it for a purpose. Right now we're just learning the rules to practice. Our last property is whenever we have a base raised to a power and then it is also being raised to a power, so a power raised to a power. And in that case, it's like we have this x to the third times x to the third times x to the third times x to the third 5 times. So I end up multiplying the powers. So this would really be x to the 3 times 5. And we saw this when we were solving exponential equations the last 2 days. We would end up with x to the 15th. So this is probably the weirdest one, but it's my favorite. I think it's the most fun. That if I have a log where in the argument there is a power, then when I'm expanding, I am allowed to move that power out front to where you're multiplying a power times a power. So remember, the log itself is an exponent, and then the y in this case is also an exponent. So if you are multiplying a power times a power, that would look like y times the log base b of x. So anytime I have a power in the argument, an exponent in the argument, I'm allowed to move it out front and multiply it by the whole log, which is kind of nifty. So the last one here, using everything that we know. First of all, if I have this 11x all raised to the second power, I can either raise 11 to the second and x to the second and then expand them, or I can move the 2 out front right now. I just have to make sure that I attribute the 2 to both. So here's what I mean. If we're moving the 2 out front right now, we've got a 2 log base 3 of 11x. If I'm expanding completely, I still have multiplication in the argument. So thinking through, okay, multiplication expands into addition. Whenever I expand into addition, so I've got 2 log 3 of 11 plus, I want to make sure that this 2 is still attributed to the x, because at the beginning, the x was being raised to the second as well. So I need to make sure that if we went back the other direction, in some ways it's kind of like factoring. You can always go back the other direction and check if we were to put this back where it was, make sure that any exponent is going to be back with the numbers that were being raised to that power. So the alternate way would be if you went ahead and raised each of those, it's going to log base 3 of 11 squared, x squared. You could go ahead and raise them both to that power and then expand into addition. So we've got a log base 3 of 11 squared plus log base 3 of x squared. And then we could move the 2's out front. So notice the 2's are in front of both. And either method is fine, just don't forget to have that 2 involved. You might notice right now that whenever I'm having this like 11 squared, that's 121, and so you might be wondering why I'm not like simplifying that. We're just working on the properties, so we won't be multiplying things out or actually raising things to powers. So I'm trying to expand using the properties. It's honestly a little bit easier if you have all variables, because then you're not tempted to do that. Okay, so I want you to try a few on your own. Go ahead and pause the video, try these both on your own. You're expanding them completely, and then we will try condensing. So pause it. I'm going to show the answer. If you don't want to see it, make sure you pause the video. So I really went for one of each type of method. In the first one, I went ahead and raised a to the second and b squared to the second, but you could have moved the 2 out front first and then expanded into addition and moved my exponents out. So you should end up with a 2 out in front of log base 4 of a, because a was being raised to the second power, and then a 4 out in front of log base 4 of b, because b was being raised to the 4th power, b squared, and then addition in between because they're being multiplied. For 2, I went for the other method, moving the 3 out front first, which is where we have to remember to attribute that 3 in front of the log base 6 of 12 and in front of the log base 6 of x squared, but it is subtraction in between because we expanded out of division. And then in the end, you may not have known what to do with the 6 if you went this direction with it. If I ever have a coefficient in front of my log and then I have an exponent that I move out front, it's all multiplication, so I'm just multiplying my exponent 2 times 3, which we could see if we went the other route, that 12 is being raised to the 3rd, so there's a 3 out in front of its log, and then x would be raised to the 6th, so there's a 6 out in front of its log. Once you get good at expanding and you understand the properties, condensing is very easy, and really this is where we're headed. We will condense more than we will need to expand, but again, once we understand expanding, this is very easy. So I'm going to start by looking for, if I have subtraction, I know I can condense that into division. If I have numbers outside of logs, then those can be inside the log as a power. And it's a lot easier to know when I'm done with condensing, because I'm not done until I have one log. So once I have everything inside of one log, no numbers outside of it, I know that I'm done. So I'm going to start by moving my 2 into the exponent of the first log and my 12 into the exponent of the second log. And then, because I have subtraction in between, I will condense them into division. So I've got an x squared over y to the 12th. And so this is perfectly fine. You can stop there. If you want to go further, you can notice, okay, they're both raised to even powers. So this would also be equal to log base 4 of, we could take a 2 out of both of those powers and then raise it to the second, because my x to the second and then y to the 6th to the second, kind of like simplifying fractions, but taking a power out of the powers. This is perfectly fine as well. Both are acceptable. Okay, go ahead and try number 4 for yourself. Pause the video because I'm going to show the answer. Try it for yourself, or at least think through what you would do. Okay, so this one, you should have, there was only one number on the outside, so moving that 4 into the power for z to the 4th. And then because we have all addition in between, that means that we condense into all multiplication. So we've got this log base 3 of x times y times z to the 4th. The last thing that we're going to look at is one way that we could apply these properties. What's important to note here is that it is not necessary to use the properties in these cases, but you can, and it is interesting. We will get to some types of questions where you have to use the properties, but this is just like that's an interesting way to approach it. So looking at the first log base 2 of the square root of 32, remember that anytime we have an exponent in the argument and our root definitely has an exponent, our square root of 32 is 32 to the 1/2, I am allowed to move that power out front. So I could have 1/2 log base 2 of 32, And then log base 2 of 32 is something that we can evaluate because it's asking us 2 to what power is 32. So going through, okay, 2 to the third is 8, to the fourth is 16, to the fifth is 32. So I have a 1/2 times 5. Remember, the answer to a log is an exponent. And so this log base 2 of the square root of 32 is 5/2. Now remember, the way that we have done this in the past is to go ahead and set it equal to something, set it equal to x, and rewrite it at 2 to the x equals the square root of 32, and then changing this 32 to be 2 to a power. That still works, and in fact this is not always going to be the easiest way. Sometimes that is an easier way to approach it, but just a different way that we could approach. Similar for this second example, log base 6 of 1/36. Again, not really that crazy to raise 6 to a power equal to 1/36 and solve from there, but I can also expand. Since I'm dividing the 1 divided by 36, I can expand into subtraction. And then both of these are logs that we can evaluate without a calculator. We've got 6 to what power is 1, and anything to the 0 power is 1. And then we've got 6 to what power is 36, and that would be the second power, so it is a -2. Okay. Go ahead and try that last one on your own. You can do it. So you should get a -8. This is similar to that first one where we can move that exponent out front. And then the log base 3 of 9, we're saying 3 to what power is 9, and that would be the second power. So replacing the log with its exponent and then multiplying, we get a -8.